Welcome back to the deep dive. Today we're tackling something really interesting, a specific chapter from the Feynman lectures on physics, chapter 35. It's all about color vision. And this is where physics gets, well, personal. It's not just about forces and fields out there, it's about what's happening right inside your own head.
Hmm.
Yeah, our goal here isn't just reciting facts about light waves. We want to really understand that connection between the physical reality, electromagnetic radiation, and how we actually perceive it. How does this infinite rainbow of wavelengths get boiled down to red, green, blue? It's this incredible mix of physics, biology, and honestly, psychology, too.
That's exactly it. That mix is why this chapter is, well, so fundamental. To really get vision, you have to follow the light energy, right? From the moment it hits your eye through the lens back to the retina, and then crucially, how that becomes a signal in your nervous system. So we're going to break down the eye structure, the different kinds of receptors we have, and the really surprising experiments that show why we sense color with just three basic components. Let's start right at the front door, so to speak.
Okay, so let's dig into that initial path. How light gets to the back. It seems pretty direct, right? Light comes in, goes through the outer layer, the cornea, that's the clear bit, then is focused by the lens, which can change shape a little, and then bam, it hits the retina. This amazing sort of sensor sheet at the very back of the eyeball. That's where the light gets turned into, well, nerve signals.
Exactly. And when you zoom in on that retina, you immediately find these two different kinds of cells that detect light. They really show the two sides of our vision. First, you've got the rods. They're incredibly sensitive to light, really, really good in the dark. They're packed mostly around the edges of your vision, your peripheral vision. And here's the key thing. They only see in black and white, or shades of gray. Differences in brightness, that's it. In bright daylight, they're completely overwhelmed, basically useless.
Right, right. That makes total sense. You walk into a dark room and it feels like your side vision kind of kicks in first, but everything looks grayish, muted. So what about seeing sharp details and color?
Ah, that's the other type, the cones. Now, these need more light. They're less sensitive than the rods, but they're jammed together right in the middle of your retina, in this tiny spot called the fovea. That's where you get your sharpest vision, all the fine detail. And crucially, all your color information comes from the cones. You know how your eyes are always making tiny movements? You're constantly shifting to get the important part of the image right onto that little fovea.
It's an amazing setup, but it also leads to something kind of weird that we usually don't notice. The blind spot.
Right, it's sort of a necessary flaw in the design, if you will. All the signals from the rods and the cones, they need a way out. They all bundle together to form the optic nerve, which goes to the brain. And the exact spot where that nerve bundle exits the back of the eye, well, there's no room for any rods or cones there.
But you don't see a black hole in your vision. It's incredible. Your brain is just so good at patching things up using the information from around the spot. It fills in the gap based on the background. You're basically unaware it's even there unless someone shows you a specific trick to find it. The brain just papers over it. Okay, so we have these two systems, rods and cones. And how bright the light is determines which system is really running the show. In bright light, it's cone time. We see everything sharp, colorful. But as it gets dimmer, the rods start to take over because they're so much more sensitive. And suddenly, the color just drains away. We're back to shades of gray.
And this switchover does something really interesting to how bright things look. It's called the Purkinje effect. It happens because rods and cones aren't equally sensitive to all colors, all wavelengths of light. Your cones, the daylight guys, they peak in sensitivity somewhere in the green-yellow part of the spectrum. But the rods, your night vision system, their peak sensitivity is shifted way over towards the blue end of the spectrum. So think about this. Imagine red flowers and blue flowers side by side in the afternoon sun. They might look equally bright, equally vibrant. But as dusk falls and your vision starts shifting from cones to rods, that red flower starts to look much, much darker compared to the blue one. The blue things seem relatively brighter, more prominent, even though the actual light hitting them hasn't changed its ratio. Your perception of their brightness changes.
Wow. Yeah, that explains why things look so different at twilight. Your brain is basically switching between two different cameras, each with its own color filter almost. And the dynamic range difference is huge, right? Like 1,000,000 to 1 sensitivity difference between the two systems. It's wild.
It is an incredible range.
So the eye adapts to brightness, switches systems. But this brings up a really deep question Feynman tackles. Physically, light can be any wavelength, right? There's an infinite number of possible colors in a pure spectrum. So why? Why does our experience of color seem so much simpler? Like it's built from just a few basics.
That's the core puzzle and maybe the most profound point in the chapter. The physical world gives us this infinite variety of wavelengths, but our internal experience, our sensation, collapses all that complexity down. It turns out the eye only responds in a limited number of ways. Astonishingly, you can basically recreate almost any color sensation we can experience just by mixing three specific colors of light. Usually we think of them as red, green, and blue. You can picture this right. Imagine three projectors, one red, one green, one blue, shining overlapping spots on a screen. If you just overlap the red and the green and you fiddle with how bright each one is, you can make yellow, or orange, or greenish yellow, all the shades in between. It means we can think about any color sensation mathematically, almost like a recipe. Yellow sensation, a certain amount of red signal plus a certain amount of green signal.
So you're not actually seeing a yellow wavelength light necessarily. Your eye is just getting the same signal as if it were. It's being tricked in a way. And this leads to these fundamental rules, the two great laws of color mixing.
Exactly. These laws basically confirm that color mixing, for our perception, works in a simple additive way. The first law says, if you have two different light sources, let's call them X and Y, and they look exactly the same color to you, even if they're made of different wavelengths, and then you add the same third light, Z, to both X and Y, the results will still look identical. X plus Z will match Y plus Z.
Okay, so the eye only cares about the final combined signal, not the ingredients list of wavelengths.
Precisely. And the second law is even simpler. It says if you've made two separate matches, say light A matches light B and light C matches light D, then if you add A and C together, that new light, A plus C, will perfectly match the combination of B and D, B plus D. It confirms this additive property. Color sensation behaves like adding vectors, mathematically speaking, which is huge.
Okay, if color is additive and boils down to just three responses, that sounds like something you could map out, right? Geometrically.
Exactly. And that's what the standard chromaticity diagram does. It's basically a map of all possible color sensations. Since any color can be defined by the proportions of those three primary responses, red, green, blue, we can kind of ignore the overall brightness for a moment, and we can represent every possible hue and saturation level on a flat, two-dimensional chart.
What does this map look like, and how does that mixing rule work on it?
Well, it's kind of a horseshoe shape or maybe like a rounded triangle. The boundary, that outer curve, that represents all the pure spectral colors. The pure colors of the rainbow, like from a prism. Violet at one end, looping around through blue, green, yellow, orange, to deep red at the other end. Every single color sensation you can possibly perceive lies inside that curved boundary. And right near the middle of the whole thing, that's where white light sits. The mixing rule is beautifully simple on this map. You pick any 2 points representing two different colors. If you physically mix light of those two colors, the color sensation you get will always fall in the straight line, connecting those two original points on the diagram. If you mix them in equal amounts, the result is smack in the middle of that line. Change the proportions and you slide along the line.
Got it. So the diagram isn't just a pretty picture. It's a mathematical definition of the limits of our color perception, all based on those three signals. It really maps the physics of sensation. Okay, so we've got the math, the perception. But how does the eye physically do this? How does it achieve this three-component detection? This brings us to the big idea, the Young-Helmholtz hypothesis, right? The idea that there must be three different types of cone cells, each type containing a different chemical, a pigment, that absorbs light differently across the spectrum.
That was the hypothesis, yeah. And confirming this is tricky, mostly because the absorption curves of these three pigments overlap quite a bit. It's not like one only sees red, one only green, one only blue. It's messier. Researchers had to get clever. One method they developed was the flicker technique. The idea is you flicker a light of a certain color really fast. If you adjust the brightness of another flickering light just right for a cone type that isn't very sensitive to the first color, the flicker seems to disappear at a specific frequency. It lets you kind of isolate and measure the sensitivity of the other cone types that are seeing the flicker strongly. It's a bit complex, but effective. But perhaps the most compelling evidence for three pigments came, ironically, from studying people who don't have normal color vision. People with color blindness, or dichromats. It turns out most common forms of color blindness happen because one of those three-cone pigments is either missing entirely or it's faulty. For example, protanopia. They have trouble distinguishing reds and greens because their red-sensitive pigment is essentially gone or broken. Their color world is built from just the green and blue signals.
Deuteranopia also confuse reds and greens, but for them, it's the green-sensitive pigment that's the issue. The fact that the problem is almost always just one pigment missing. That strongly supports the idea that normal vision relies on all three working together.
So, what are these pigments chemically? Are they related to the stuff in the rods, the visual purple?
Yes, they're chemically similar to visual purple, the pigment in the rods. And figuring this out directly was a real challenge. But in the late 50s, a researcher named George Rushton pulled off this brilliant experiment. He actually measured the absorption of these cone pigments in a living human eye. He did it by shining bright colored light into the eye, which bleaches the pigment temporarily, uses it up, basically. Then he measured the faint light reflected back out from the retina. By seeing how much light of different colors was absorbed while the pigment was being bleached and recovering, he could actually plot out the absorption spectrum for the different cone pigments. He could even measure the spectrum of the pigment that's missing in protanopes, confirming it was distinct. It was this amazing physical confirmation, closing the loop. The three-component sensation really does come from three distinct chemicals in our cones. Hashtag Hagnat outro. So yeah, we've covered quite a journey here, from light hitting the cornea and lens to the two parallel systems of rods and cones in the retina. And then figuring out that color sensation is additive, built on three components, mapping that entire world onto the chromaticity diagram, and finally pinning it down to the actual chemical pigments in the cones. It's quite a chain of logic.
Absolutely. And that core idea just keeps coming back. Color isn't some absolute property of the light wave itself. It's this incredibly sophisticated interpretation, a sensation that our brain constructs based on signals from just three types of sensors. It lets us see countless physically different combinations of wavelengths as the very same color. It's physiology simplifying physics, in a way.
Okay, so to leave you with something to chew on, building on all this, consider the color brown. We've established color is about hue and saturation, mapped on that diagram. Brown physically is just dark yellow or dark orange.
Right.
Low intensity light from that part of the spectrum. So given the precision of the diagram, the three-cone responses, why is the idea of brown, a color you never see in a pure spectrum, a color that needs context? Why is it so fundamental to our psychology? Why does it feel like a distinct color, even though the physics says it's just dim yellow-orange?
That's a great question. A good reminder that the story doesn't end with the physics and physiology. There's still the perception layer on top. Well, thank you for joining us on this deep exploration into how we see the world in color.